we are diving straight into one of the absolute highest stakes areas of the Cambridge physics syllabus, linear momentum and its conservation. No fluff today, we are getting right to it. We're going to break down exactly how this core principle operates, not just in simple one-dimensional examples, but in complex 2D scenarios. We're going way beyond the basic formulas here. We're going to decode the mark schemes, figure out how examiners test your actual grasp of the physics, and build a systematic attack plan so you know exactly what's happening when objects collide. Let's look at the raw data for a second. 15. That is the magic number. Linear momentum and its conservation accounts for roughly 15% of the total marks in paper 2. Think about that. 15% of your entire grade is on the line with this one single topic. It's a massive chunk of marks, which really just goes to show how foundational this concept is to the rest of physics. If you want to master classical mechanics, and honestly, if you want that top grade, you absolutely have to lock this down. But here is a really painful reality. Why do top students who know all the equations backward and forward, completely bomb when they face unfamiliar two-dimensional momentum contexts? Why does a question that looks even slightly different from the textbook completely derail them? Well, it's because they treat it like a memory test. But the physics of momentum isn't about memorization. It demands a really deep analytical grasp of how vectors actually interact in physical space. When you're forced to resolve forces and velocities across multiple axes, rote memorization just crumbles, and making that mistake is going to cost you the A grade every single time. Okay, let's dive into this. What is the fundamental physics here? Linear momentum is defined as the product of an object's mass and its velocity. Simple enough, right? P equals m times v. But the real heavyweight principle is the conservation of linear momentum. This tells us that in a closed system where zero external forces are acting on it, the total momentum remains absolutely constant before and after a collision. You need to understand this causal relationship deep in your bones. Recognizing that velocity is a vector, meaning it has a very specific direction, is literally the theoretical architecture of this whole topic. You need precise, logical reasoning here, not just superficial breadth. Now, because these calculations can get incredibly complex, especially when you're trying to figure out if a collision is perfectly elastic, where kinetic energy is conserved, or inelastic, where it isn't, there is a massive saving grace. I like to call it the method mark strategy. Cambridge examiners actually award marks for your process. That means your final calculated answer could be totally, completely wrong due to some tiny arithmetic slip-up, but if your physical methodology is logical and, most importantly, visible on the page, you are going to secure the majority of those marks. It is an absolute game changer. So how exactly do we guarantee we get those method marks? We use a ruthless 5-step procedural framework every single time. Step 1. Deconstruct the question. Are these objects colliding and sticking together, or are they bouncing apart? Step 2. Extract the data. Hunt down those masses, initial velocities, and critical vector angles. Step 3. Select your framework, which usually means setting up the equation where initial momentum equals final momentum. Step 4. Execute your vector notation. You have to be hyper-aware of your positive and negative directions here. And finally, step 5, present your final values using the correct terminology. It's like building a step-by-step physical model of the event right there on your exam paper. In a moment, I'll show you the examiner clue that changes the answer completely. But first, you need the framework that makes that clue obvious. You see, to make these physical clues actually stand out in a messy, complex scenario, you have to understand how the assessment is built from the ground up. And this brilliantly illustrates the ultimate answer pipeline required for top marks. It's a 4-step evolution. First, you identify the core physical concept, like conservation of momentum. Second, you lock that down with evidence and data from the prompt, the exact masses and initial speeds they give you. Third, you employ scientific reasoning. So maybe you're explaining why kinetic energy is lost as heat or sound because it's an inelastic collision. And fourth, you translate all of that into precise examiner wording. If you build your responses across these 4 pillars, you are proving to the examiner that you have a rock-solid understanding of the physics. All right, we are escalating things now. We are officially entering the hardest area of the syllabus, the 2D momentum boss fight. One-dimensional momentum, where everything moves in a nice, neat, straight line, is just your basic training. 2D is where they ruthlessly test your vector skills. When a particle explodes or 2 objects glance off each other at strange angles, momentum is still conserved, but it's conserved in the x and y directions totally independently. You have to reverse engineer this boss fight by resolving vectors using trigonometry. So the momentum along the x-axis is the total momentum times the cosine of the angle, and the y-axis uses sine. You are literally setting up two separate realities, horizontal and vertical, and solving them both. Now, what's really interesting about this slide is seeing the contrast side by side. Look at the flawed student response versus a flawlessly reverse-engineered top-band answer. The flawed answer is vague. It completely fails to assign negative signs for opposite directions, it shows zero working, and it completely ignores the independent X and Y components of the specific context. It's a disaster. But the top-band answer, it clearly resolves those horizontal and vertical vectors, it identifies the exact physical differences, justifies its steps, rigorously maintains the sign convention, like establishing that left is negative and right is positive, and carefully executes the final resultant velocity using the Pythagorean theorem. That is what analytical depth looks like. If I put on my senior examiner hat for a second, let me reveal the top 3 fatal errors pulled straight from the principal examiner reports. These are the traps that cost students their grades every single year. Number 1, answers are just too vague. You have to explicitly state your principles. Confusing elastic and inelastic collisions is a classic vague mistake. Number 2, students completely forget to check their format and presentation. That means they drop their negative signs for reverse directions. Remember, vector direction is absolutely crucial. And number 3, answers are not specific to the context given. You can't just memorize a generic response, you have to tailor your math to the specific collision happening on the page in front of you. I am going to say it again because it is just that important. Students lose marks by not showing working. Even if your final answer is totally wrong, method marks can save you. The Cambridge Assessment Framework doesn't just want a single number at the bottom of the page, it prioritizes analytical depth. Deconstruct the problem, solve it, and evaluate it systematically. Leave a massive, obvious trail of logic on the page. Show every step, from resolving those tricky angles with trig, right down to combining the final velocity vectors. Prove your competence, and the marks will absolutely follow. So wrap your head around those core takeaways. P equals mv, momentum is always conserved in closed systems, and break those 2D collisions into independent X and Y axes. And if you want to keep mastering these frameworks, subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations. We have a whole library of these explainer deep dives waiting for you. So you've survived the 2D boss fights today. You know the vectors, you know the conservation rules, and you understand the method mark strategy. But here's the ultimate question to leave you with. Do you know the exact command words that actually decide your mark band? Because if you don't know the examiner's difference between state, explain, and evaluate, all that physics knowledge won't save your grade. Understanding command words is your absolute mandatory next survival step. So what do these words really demand from you? Well, that is exactly what we're tackling next time.